let's do this midterm then. Let's start with the first question. Does everybody have it in front of them or have access to it? No? Okay. Well.
We'll take pictures of it.
No, I mean, just so you know what the question is while I'm doing it. So this is going to be midterm 2015. Right, good. Resolution is so bad on that. Oh my god. I should hope so. Okay, so 1A asks to write the general frequency domain Maxwell's equations in the point form. So in the point form means without integrals and all that, so that's the form that we're used to seeing them the most, especially when he's doing all the stuff on the board. So we want frequency domain. I should point out, before I get into this, there are marks taken off for vector signs, everything, pretty much. For vector signs being missing. He takes off, I believe, a quarter mark for every vector sign you miss, up to 4 marks in total. And at the same time, subscripts. So, for example, when we write in the frequency domain, we write Maxwell's equations. So I'm going to write Maxwell's equations in the point form. In the frequency domain, I write ES to denote that it's in the frequency domain. And then we write, obviously, BS. Like that. And so if you're missing a vector sign there, if you're missing the subscripts there, then you've automatically lost 1 mark right now. So the question is apparently this part's worth 1.5 marks. So you've only got half mark for that if you missed your vector signs and you missed your subscripts. So don't forget your subscripts, don't forget your vector signs. So that's equation 1. Now the next one, I usually like to write Ampere's law. So then we write Js plus j omega ds. Next one, Gauss's law for the electric field, let's say. And this is rho v s in general in the frequency domain. And finally we have Gauss's law for the magnetic field, so to speak, and this is that. And so I believe, how many marks is that? I don't know. It's like 4 or 5 marks right there, I think. 1.5 for 2 of them, 2, 3, so that's 3, 6 marks right there. So study this stuff carefully. Easy marks. That is part A. Yeah, okay. So, yeah, general frequency domain in the point form. Now we want them in the integral form. This is where people get a little confused about stuff, because integrals suck, apparently. So for the integral form, I usually like to remember, well, I mean, over time you'll kind of just remember them off the top of your head, but I think the one that people tend to remember the most is Ampere's law, just because it's so easy to use in everything that we use it for. So let's start with Ampere's law. So we have Hs dot dl, and this is L, and then this thing usually we call it, we can call this Js plus, what is it? No, that's time domain. So j omega ds, like that. But now the thing is we need to integrate this thing, of course. And he's done it a little differently here, but I'll show you both ways. So we have this integral, should be over a surface, and, well, I don't need to put the dot there. Should be over the same surface there. So now the way he's done it is instead of calling it Js, he's called it Is, because he's calling it the current, because once you integrate Js over the same surface, it'll be I. Yes, your question? Js is usually conduction, convection, and impressed. So those 3 usually fall under Js, but typically we say in general it's those 3. Assuming he tells you which one it is, then you just break it down into that one. So if it's conduction, it'll be sigma E. If it's impressed or convection, he won't tell you, because there's no equation for those. Those are experimentally measured. Question?
For the integral with the circle?
Yes, closed loop.
Closed loop?
Yes.
I remember hearing like early in the semester that you had to be an arrow for the circle. Yeah, it's like you lose a mark if you don't do the arrow.
He does that.
He does. He does do it. He does do it. Okay, he does do it. So let's draw the arrow, guys. Let's draw the arrow. We don't want to make anybody mad. Okay, so there's an arrow. Thanks for pointing that out. So do the arrow. I have no idea what the arrow is there for, but do the arrow. Yes.
Isn't there like a line picture?
Yeah, there's a line there too.
A line for the current?
Yeah.
Holy hell, he does do that. What the hell is that?
It's like direction of.
Okay. Look, I'm just gonna do it the way he's done it because I don't want you guys coming here after and saying, "Hey, what the hell? You did it that way." So hey, I'm gonna do it exactly the way he does. He does this, and there's like this little wiggly arrow thing. I don't know what the hell this is. Okay, apparently that's the equation. So essentially, the way to know if you've gone back and forth between this is if anyone remembers Stokes' theorem and Green's theorem. Stokes' theorem essentially says this: in general, if I have something along the closed line, like this. No, I'll use a different letter so it's general. A dot dl becomes the same thing as this thing if I take the curl of A across the same surface that the thing encloses. So now you know how to get back and forth. You should know that they look similar. So you can actually end up transforming what's inside the integral to use this curl equation and then go back and forth. Do you need to do that? No. Can you just memorize it? Yes. Do whatever you want. If you want to memorize it, sure. These equations you should probably have memorized at this point just because they're so basic, and you will use them for everything. Okay, so I usually like to start with Ampere's law, then we'll go into Faraday's law, which is the next easiest one I think to remember. Now we have to remember our arrow. Apparently that's a thing. So now we have, this is ES, cross this closed loop, and this is equal to minus j omega. Does he have any crazy shit? He apparently, okay, sure. I don't know what this is. I don't know. But that's not an S. What is that? Okay. Anyhow, I don't know. He wasn't this anal about it when I did it. This is S. Sorry? Look, whatever he does, just do it. Okay? I don't know what he does. Whatever he does, do it. I'm just gonna go through it step by step and do it this way. If you're gonna pick the little details and all that kind of stuff, I guess you can add on your own. But what we're here to do, I guess, is to go over concepts you have questions about. You can ask him about the arrows and all that stuff, because I don't know what the hell that's all about. I'm just as confused as you are. Okay. And so next we have Gauss's law. So this one is a closed circle, because it's around a surface. Apparently it's the difference. So we have D, S, and I should hope that everyone has these laws. They understand what these mean, and it's not just that we're writing a bunch of equations. Because they are fundamental, and because we are electrical engineers, and we should know something if we've done 4 years of school. If you know anything by the end of your 4 years, I let it be Maxwell's equations. You know, it's useful stuff. It makes you look a lot cooler than you actually are if you can write these equations. And you can explain them. Okay? So here we've written in the integral form. Now it says correlate each of the obtained frequency domain integral form equations to its corresponding point form. So literally just put arrows between them. Which one corresponds to what is what he's asking. So if I write 1 here, then that corresponds to 1 here. If I write 2 here, that corresponds to 2 here. And so on, and so forth. Which is 2 marks. 2 marks for that. Just drawing connection. So make sure you know where they are. Next is what? Write the constitutive relations in the frequency domain for isotropic regions. So first we have to know what the constitutive relations are. Pretty much it's how we relate D and E and then B and H. So they're related by their constants of permeability and permittivity respectively. Literally all he wants is ds equals epsilon es. Yes. No, I'm recording it. Somebody asking? Oh wow, I forgot to tell them. Totally hung them out to dry. But yeah, if anybody has access to a computer and you can go online to the Twitch stream and just tell them I'm not streaming this, but I am recording it. Just because streaming last time we had some issues with, rather than run into the same issues, I'm gonna try recording this time. I'll post it on like YouTube or something because I don't have access to D2L or Black, whatever the hell it is. And then so here we have Bs equals mu Hs. Now notice in general this is epsilon and mu because it tells us that it's an isotropic region. So we know that it's not free space. We know that it's not something where you might have mu naught or epsilon naught. So isotropic regions, we generally assume that mu and epsilon are in general those values and not epsilon naught. So that'll be epsilon r times epsilon naught, and mu will be mu naught times mu r. Also, there's nothing complex about epsilon because we know in general that permittivity can be complex. So it's not complex because it's telling us that it's isotropic. I would suggest you go through the textbook to find out what all those type of things, linear, isotropic, homogeneous, all those things mean. Because again, he tells you he tells you that the thing is that, but doesn't tell you what that implies. So you should know that on your own. I think, I don't know, something like that. I went through like certain conditions, if it's conductor, if it's this or that. So just look at my notes, I guess. I simplified that's straight from the textbook. So if you look at the textbook, you'll find the same thing with more information. Sorry, that was D. That was not C, that was D. Now part E asks to simplify the frequency domain Maxwell's equations obtained in part A for linear, isotropic, and homogeneous and charge-free regions, taking into consideration the constitutive relationship. So pretty much he wants you to rewrite the equations entirely in terms of E and H, or B and D. Typically we write them in terms of E and H because those are the parameters of interest and they mean more twist than flux density. Because flux density can change based on where you are, and then but the intensity relatively stays the same, more or less. So if we do that, we take into account that, well, first let's go ahead and write our equations out. So we have ES equals minus j omega BS. Now we know that BS equals mu HS. Am I writing? Is that big enough? Is that okay? For the last time we had issues with the size. So essentially you take this and you substitute that into there, and so now we have the curl of E S equals minus j omega mu HS. And so he literally wants you to do this for every equation. So we do the same thing for Ampere's law. So we come here and we get, this is Js plus j omega ds, and essentially we're going to plug in d equals epsilon E into ds. And so I'm guessing what he's going to set up for the next equation, under the next question, is to derive the wave equation, because this is what we usually do when we're setting, when we're deriving the wave equations. We express everything in terms of E and H, so we know that this is true, and so then we can say that this. No, that's not the one I want. Wrong one. I want d s equals epsilon E s. And so then I have the curl of HS is J S. I suppose I can probably simplify this too. Yeah, I can. So let's do that too. So, sorry? Exactly. So we have epsilon ES. Let's write your subscripts. So then we have curl of HS equals sigma ES plus J omega epsilon ES. Hope I've done that right. I have. Okay, so he goes on to simplify it further and says epsilon E equals epsilon, and so pretty much factors everything out. Is that necessary? I don't know. Let's go ahead and do that anyways. Just because. Oh no, there's an I here. Because this is JSI. What does the I stand for? I don't remember. But it stands for something. Sorry? Is it imperfect? Thank you. There we go. Imperfect. Maybe you should be just teaching this. That's good. It's good that you're remembering that at least. So essentially what we can do now is we can factor things out, and we can... well, no, he doesn't factor out. Well, here's what he's doing, because he's in general. He wants this done in general then. Okay. So he does this. He writes epsilon E. And so essentially epsilon E... What's the region again? So it's linear, isotropic, homogeneous, and charge-free regions. So epsilon E is going to be epsilon times 1 plus sigma over j omega epsilon. I'm not entirely sure why he's considering a conductivity, even though Well, he hasn't says it's a dielectric, so yeah, I guess that's fair. If it says it's a dielectric, then we know that sigma is negligible. Okay? Because when you have a dielectric, it doesn't really conduct. Do you all know that? Is this making sense? I'm seeing a lot of blank faces. That's what I said. Does anybody have questions?
No, like
I don't have access to it on D12, or else I would just show you guys on my thing here. Do we have a document camera? Doesn't open. They're not. Does my card open this? Because I don't have the. That's what I'm saying. I was asking if anyone has it. You can pull it up on your computer or something. Did he post it or no? What's the number? Oops, I'm recording now. Does he? No. Yeah, he's such a scumbag like that. I don't know why he does that. So you know, I can't. Sorry? Yeah, email it to me. So somebody can email it to me. Well, I don't have Facebook like that. I'm not active on Facebook. But yeah, email it to me. I can pull it up here. So yeah, everybody pull out your phones and look at Facebook. Okay, so that's it for this part. So what I'm going to do is I'm going to go to the next equations. Because I think this is really the only sort of iffy part. So we'll come back to this. I'm going to underline this in orange. We'll come back to this part. So now, the other equations are simple because I have this divergence of ds equals rho vs. And so essentially all we do here is we look at the question. Question says it's charge free. So that tells us what? Anybody? I'm sorry? Rho vs what? Is 0. Yes, right. Understood something, nailed it. Free means rho vs equals 0. I'll put that in red because that's not something we're coming back to. So then we say that, then we know that d is epsilon e. So then I can call this epsilon e s. But now because the other side equals 0, does he do that here? Right. Because the other side, the right side equals 0, we can divide out epsilon, because epsilon doesn't depend on space, we assume, because it's linear. If the region is not linear, then epsilon depends on space. But the region is linear, and so that's why we always assume epsilon is constant. Since epsilon is constant, then I can rewrite this as just the divergence of E equals 0. Probably do something here like this, so that we can actually realize these notes are so messy. Okay, and now we have one more, which is probably the easiest one, is this divergence of Bs equals 0, B equals mu h, Bs equals mu hs. Same thing applies, because it's linear region, we assume that mu is constant with space, so we can divide that out once we substitute it in. So I get mu hs equals 0. And then I get the divergence of hs equals 0. So, does that all make sense? If there are any questions, please ask me, because the point of us being here is to ask questions, not to just sit here and think I'm some big, scary guy like the professor who doesn't want to answer questions. So all that makes sense? More or less. Which is it, more or less? There's one more part to this question, I think. There we go. So now it says, and I guess this is where majority of the marks are earned. 12 marks. So that all, pretty much everything we've done so far is worth 26 marks. Right? So, well, I mean, but these equations, these are things we should know off the top of our head, I think, at this point. You should know these equations. Like I said, I should be able to wake you up at 3 in the morning and ask you what these are. You should know. The next part, sure. Yes? I would, because in general, if it's it doesn't say what type of region it is. It doesn't say if it's a dielectric. If it's a dielectric, we know that sigma ends up being 0, so that second term goes away. But the thing is, if it is something that's conductive, then that imaginary term will be there, and there will be that sort of phase difference because of the J term, right? So in general, yes, leave it there. If it says it's a conductor, then you can get rid of it. Sorry, if it's not a conductor. So if it says it's a dielectric, sorry, that's what I meant to say. If it says it's a dielectric, then you can get rid of that term, because you know that sigma is going to be very small in that case. So it's not going to be important. If it's a dielectric. If it says it's a dielectric region, which he probably won't tell you, because if he does, there's no point asking that question. Then at that point, like the whole question really just breaks down to, can you substitute one equation into the other? So it really doesn't test anything you know. So chances are he's gonna if he does ask you something like that, he'll ask you. He won't mention what kind of region it is. He'll just say it's linear, homogeneous, isotropic, whatever. He won't say it's a dielectric or a conductor. I'm saying you should include that. I mean, come on, it's like 2 steps. You can do it. I believe you can do it. I believe in you. You have it off there. In Ampere's law? Because we want everything in terms of, it says everything in terms of the constitutive relationship. Simplify it, says obtained in part A for linear, taking into consideration the constitutive relations. So you want it to be as simple as possible. You want everything, like I'm saying, he's setting it up so you can solve the wave equation. And sure enough, the next question is to solve it. I mean, it's just because we use these things when we're solving that. So yeah, I mean, it's in the most general form. You're considering the region. You're describing the region essentially with these equations. So now, part F. Yes. Because you can divide it out. The reason is because it's a linear region, meaning it doesn't depend on space. If it's not a linear region, which it'll never be in this case, then you can't divide it out, because that curl is going to affect epsilon as well. In this case, the curl doesn't affect epsilon. So we can pull that out and then just divide it. Okay. Oh, part F. Where will we take it? I think that's good. Let's do 2 lines. So it says use the needed simplified Maxwell equations of part E. It's supposed to say derive, but he wrote drive. Derive the wave equation in terms of the frequency domain magnetic field intensity Hs and the propagation constant. In the process, determine a simplified expression for the propagation constant. So essentially what he wants us to do is derive the wave equation. And like I said, I told people who were in my sections for labs that it'll probably almost be guaranteed to be on the test. And sure enough, it was on last year's test. So does anybody know how to do this? Okay. So we always start, well, it depends which one we're deriving in terms of. Here we're deriving in terms of H. So if we're deriving in terms of H, we start with Ampere's law. Hold on, wait, how's he doing here? How do I want to do this? Okay, so here's what I'm going to do. There's a number of ways you can do it. He does it a different way. I'm going to do it a different way. So, because you'll have his solution and then you'll have mine as well. So then you have plus J omega epsilon E S. So this is just Ampere's law that we simplified above, right? This right here. So the next step is what we do is we take the curl of both sides. Okay? Does he give the vector identity? No, he doesn't, so you're screwed. No. The vector identity, I guess you can memorize that, because it shows up on the thing. So I would suggest going home, when you go home, make sure you derive this equation on your own. Because again, I told everybody it would be on there, and sure enough, it's on last year's. I'm pretty sure it'll be on this year's as well. Somehow people still manage to mess up on it. So essentially what we do is we take the curl of both sides. Okay. Cool. Now, the identity is actually is it some frequency domain? If it's some frequency domain, it's a bit. So cross. What do you mean? What? Oh, you mean that you're telling me the identity?
Yeah.
Okay.
And we can do delta dot delta dot H minus delta squared HS.
Is that true in frequency as well? I know there's a second. I know there's a no. That's actually no. You're right. You're right.
Yeah, I think that's
It's no. It's this. It's negative. He puts a dot here. Just look at his answer. Why the hell am I having?
yeah.
Sorry, guys. Trying to do it all off the top of my head. Trying to be a good guy. No, I've got it. I've got it. Thanks, though. Trying to be a good guy here. So you have this gradient of this divergence. You need the dot in the middle because that's the vector. That's the vector product. So we have this thing's actually called the Laplacian, the first term, when you take the del squared. So we have the Laplacian of H, we have the gradient of the divergence of H, and this is actually, we'll pull sigma out, and then I'll write the curl of ES, and then I'll write here plus j omega epsilon E curl of ES. Okay? Okay. He did it differently. Why is he doing it that way? I don't like the way he did it. But then he's gonna take marks off if we do it my way. Oh. Because essentially what he's doing is, see how I've substituted in sigma E? Here? He leaves it as J. And then he takes the curl of that and then just brings that to the other side and leaves it there. Essentially it's the exact same thing. But... Sorry? My way is just exactly like what I've done here. I've substituted sigma E. Now what I'm going to do is I'm going to take the curl, and now I can substitute from Faraday's law. Because the curl of E is negative j omega b. So you can do it both ways. But what I'm going to do is I'm going to go back to do it his way. Because I don't want you guys getting messed up. And again...
actually I checked out Constitutive from the week like that Faraday talking about.
Is he?
Yeah, there's someone in this country.
Well, I don't know, that was a few years ago. Just times change, man. I don't know, because some TAs are, it depends on the TA. If I see it and I get it that way, I'm sure I'll mark it right. But if some other TA sees it and says, no, it's not in the solution, I don't know. So what I'm going to do is I'm going to go back, and I'm going to ignore this, but just know that it can be done this way as well. So what I'll do is, no, I won't even go that far. I'll just resubstitute that back in, okay? So I'll do this. So just in the next line, just make a note that it can be done this way, but we chose not to do it this way. So you don't have to go back and scribble everything out and get angry at me because you messed up your notes. Plus this gradient of this divergence of HS is going to be the curl of JSI. I'll make a note here. JSI equals sigma ES. Or maybe it doesn't. Maybe he's considering it to be general, so he's calling it the general current. I don't know. In any case, plus j omega epsilon E, and then this is the curl of ES. Okay? So literally all I've done is I've plugged in this JSI equals sigma E, which we know is true. Now, the thing to notice here is this is 0. Why? Because we established that right here. And so then I end up with this. Well, I know from here that the curl of ES is actually minus j omega epsilon E ES, which we established. No, it's not. That's wrong. E. It's mu HS. I know. Apparently, I forgot. It's been a long day. So. Right. Okay. So now what we can do is we can substitute that in and we can start simplifying our equation. Yes. Zoom out a little. Fine. There we go. Better. HS. So this, I'm going to take this squared, HS, I'm going to multiply the whole thing by negative, then I get minus this curl I minus this thing as well, J squared, well, I don't want to do that, so I'm going to say J omega epsilon E minus J omega mu HS. Okay. Almost done now, so we take this HS. I'm going to bring this HS term on the right side over to the left side. So that's going to become plus J squared. J squared. Well, if I put it in there, that's going to be minus J times minus J, is going to be positive J. So it's going to be minus J squared. Minus J squared is just plus 1, right? I hope. Apparently you forgot how to do complex numbers. Omega mu epsilon E HS. That's what it should look like. From what I remember. Again, I forgot that I have the answer in front of me. That is correct. And so now what we do is we define something here, and it tells us to define in the question, if you have the question in front of you, for those of you who posted on Facebook or whatever it was. It says, in the process, determine a simplified expression for the propagation constant. If anybody knows what the wave equation looks like, they know that this thing in the front here is just gamma squared. So then we define gamma squared equals omega squared mu epsilon. So then that means that gamma equals this square root mu epsilon E, it should be, because we're talking in the general case. I don't know why he's multiplied it by a J. Does anybody see a J there? No. Apparently... No, I'm missing a negative sign, that's why. Sorry, guys. No, I'm not. That's right, but then he... Oh, so here's what he's doing. He's just defining this weird. So weird. So he's defining this as J omega, and then what he's doing is rewriting this whole thing. Whoa. HS. That's just the way he's defining it. Why? I'll show you why. So the equation ends up becoming this. So it turns into minus gamma squared. That's instead of plus. Because that's the more accepted form. The thing is, the equation I'm about to write here, this is actually, this is actually an easily solvable differential equation. If it's a plus, all of a sudden everything breaks down and we don't know what the hell to do anymore. That just shows us how much we understand math, right? And so yeah, so that's why we do J omega. So the J omega essentially prevents us from having a something plus something, because that differential equation is different from plus minus. So it's just a mathematical manipulation. So what you should take away from all this is that this here is the wave equation, and if you don't have this final result, you've done something wrong. So even if you don't remember what gamma is, but all of a sudden you realize that I have something plus, or something, I don't have a minus sign in my second term, all of a sudden you should realize that I've done something wrong, because I should have a minus sign in my second term. So then you go back and you say, how did I redefine, or how did I define gamma? So that is the first question. That whole thing, what we just did right now, is worth 38 marks. This whole question is worth 38 marks. This test is out of 75. So literally, I mean, what was you do this plus like you get like part marks on the next two questions and you pass. So please pass the test. It'll make me look good. Because they're like, oh, you got into tutorials, now everyone's passing. I'm like, yeah. Look, you guys pay me something, man. Give me some money. Okay, then we have this next question about two perfectly conducting coaxial cylinders with radii A and B, and the frequency domain vector potential is given by something where C is a constant and beta is a constant. The radius of the inner is A. Yeah, that's A. And the inner radius of the outer cylinder, get that, is B. The region between the perfectly conducting coaxial blah 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 in free space is also source free. Make a good sketch in the xy plane of the cross section of the described configuration showing all needed parameters and determine a bunch of crap. The frequency. So holy crap! This is pretty much a field theory question. This should be fun. Okay, so first he wants a picture. So if anybody likes drawing, now's your chance. This is problem 2A. Problem. I'm hoping to draw it out properly for you guys, so that you guys will know. So essentially, it gives two perfectly conducting coaxial cylinders. Okay, so you have essentially one cylinder, and then you have like another cylinder around it, and it's going to go something like this. But that's what it looks like from the side, right? So what he wants a cross-sectional view of it. So this will go on for forever. So he wants a cross-sectional view. So let's use the circle tool and be fancy. And oh, there we go. Okay. And it tells us the inner radius is A, the outer radius is B. So this inner radius is A, and this outer radius is B. What else does it tell us? It tells us between these two cylinders with radius that AS is given. So apparently there is a vector potential given inside here, I believe. So it says the radius of the inner is blah 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 blah, and the radius of the inner is blah, blah, blah. So the region between the two is perfectly conducting. So this is region is perfectly conducting. What else is it doing? What? The region between the two perfectly cylinders. Oh, so the cylinders are conducting, but this is free space. Sorry. Misread that. Jump to conclusions. So that's not perfectly conducting. That's free space. Free space, but the actual cylinders are perfect conductors. Perfect conductors. So the black lines I've drawn are perfectly conducting, but the region between them is space. So essentially you have, imagine two toilet paper rolls, and you wind one up a little tighter than the other one because you have nothing better to do, and then that gap between them is free space, but the two toilet paper rolls are conducting. So if you have conducting toilet paper rolls, I want to know where you buy them from. So it says the region between is free space. It's also source free. So source free. Okay. So now this is our sketch. It says make a good sketch in the XY plane of the cross section described showing all needed parameters. I don't know what all needed parameters are because you don't really know what you need until you start solving. But that looks like it's about it. Okay, cool. He's drawn a bunch of other crap like writing EM wave and all this crap, but essentially it's what I've done here. So now it wants the frequency domain magnetic field intensity HS in the region, in that free space region based on the given vector potential. It says do not use any equation of Maxwell, which I saw this in another question that he did a couple of years back, and it's just it's mind-boggling. Like, how can you limit how I'm solving my equation? Or how I'm solving my question. The course is on electromagnetics, but you're not allowed using Maxwell's equation because that's cheating. So here's what it asks for. It asks for find HS essentially in that region between in rho is greater than A, less than B. So anybody have any suggestions? No Maxwell's equation. Tell me about it. Yep. Too complicated. It goes simpler than that. You literally take the curl of this thing. Because I don't know if you guys remember, but in one of the earlier lectures, he might have defined this. Anyone remember this? So you literally just take the curl of it, and then you b equals mu h. And so you divide b by mu, and you get h. And mu is mu naught because it's free space. So now we take the curl of this thing, and this is the cylindrical curl. And I have no idea what the cylindrical curl looks like, so I'm going to look at my solution here. So apparently it looks like this. So it's partial a rho s, and a rho is the component in the rho direction, which is all we have. Oh, sorry, I should probably write this. This is important, very important information. As is c over rho e to the minus j beta z in the a rho direction. Okay, and it says c is complex and beta is a phase constant. So c in general is a complex number. So we'll probably have to use that somewhere later on. So this is going to be partial a rho s with respect to z. And this is going to be in the a phi direction. How do you know this? I don't know. It doesn't. Maybe he gives you an extra sheet. It's not given on this thing. He does usually give curls and stuff, but not in this one. So if you do need to know that, and you don't know that, you're screwed. So yeah, I don't know how you would know that if you don't know what the actual thing is. If you don't have the actual equation, I don't know how you would figure that out, because I know people usually don't memorize this kind of stuff. Hopefully he'll give me something. Oh, but apparently that was 1 mark for making that drawing. That's 1 mark. So if you guys get the whole first question right, get this 1 mark and get 1 more, you guys pass. Or you just hope you ride the curve at that point. So you'll be good. You'll be good. So now we take the derivative of this thing. Oh, it looks lovely. And so this is going to be, our equation is c over rho e to the minus j beta z. So essentially all we do is bring the minus j beta down, and we've done our derivative. So this is going to be in the a phi. So this just becomes c over rho minus j beta e to the minus j beta z a phi. And this is b, right? And so now we know that bs equals mu naught hs, and it's mu naught in this case because it tells us it's free space between those two parts. So we know it's mu is mu naught. And so then therefore we can use that, and all of a sudden we realize that h of s is going to be minus j beta c over mu naught rho e to the minus j beta z a phi, and we don't want to forget our units, even though he forgot his units, so somebody should go point that out. Amps per meter, and that is between A and B. Any questions about that? That's like 5 marks right there. Yes. Yes. I'll extend that a bit. There we go. Okay. Cool. 4 marks. Next question. Frequency domain electric field intensity in the region based on Hs, and now guess what? We can use Maxwell's equations now. Okay, so find EF. How do we do this? There's a couple of ways you can do this. you can either take the curl of H and then equate that to J omega epsilon times E, which is just Ampere's law. Or you can take the curl of E, work backwards, and then just divide by J omega. Because we can either use Faraday's law or we can use Ampere's law. He uses Ampere's law here, so I'm just going to use Ampere's law as well, just because that way I can actually give you an answer that makes sense. And I can know it's right, and I won't waste your time. You will get the exact same answer. The answer will be identical. Like most professors say, convince yourself that it's true. So you can go home and do that, because I know you have nothing better to do. I'm sorry? Somebody said that's why we're here? Yeah, same here. I was actually just up in the lab before I came here, and one of the grad students there was like, "What are you doing here so late?" Like, "I'm doing a tutorial." I'm like, "On a Friday? Don't you have anything better to do?" I'm like, "Apparently not." So yeah, we're here. So essentially we're gonna take the curl of this thing, and then we're gonna divide it by J omega epsilon naught, and we have our ES. So again, I'm pretty sure the curl equation will be given to you because it's unnecessarily. Well, I guess it's just silly to ask you to memorize the curl equations. Not. Yes, it's free space. That's why. Free space between the two conductors, right? So we have this curl of HS is going to be minus del over. Well, this is the phi s over z in the a rho direction. But he wrote a second component, but then crossed it out. So what was the point of writing it? Oh, because it has a component, but the partial is 0. Okay, so let's write that as well, and that'll be a good lesson in this. So we have rho h phi s in the az direction. So now, so why does it cancel that? He wrote that wrong, doesn't he? I'm not too sure about this part. I think he crosses this part out. Oh no. Totally. He's totally right. He's totally right. Because what happens is when you multiply rho by this thing, let's just do it. Let's just do it instead of talking about it. So minus partial over partial z of h is what? Minus j beta c over mu naught rho e to the minus j beta z, and this is in the a rho, and then you have 1 over rho partial over partial rho times, and this is the thing I'm talking about. He writes it out, but then he crosses it out after prematurely, in my opinion. Beta z. So now the thing to note here is this is an az, is that when I multiply this, these rows cancel. And now the partial derivative of that with respect to rho becomes 0, right? So he literally just crosses it on the first step. So this whole thing is 0. But I guess it's important to know to figure that out, because if in the case that rho in the denominator is not there, all of a sudden this derivative isn't 0 anymore. So I guess it isn't. It's good to write that, and to know that's actually what happens. So now what we get is we take this derivative. Why is it 0? Because when I multiply the rows cancel. Now take the partial of something that doesn't depend on rho. It's constant. So what do I have here? Now what we have is taking this derivative, and so what we do is we multiply. So this minus times minus actually becomes j beta squared. How do I want to do this? Let's just do the way he did it. Times minus j beta, because the first minus gets cancelled out from the negative outside, and then that second negative comes down with the j beta, multiplied by c, which is our constant, over mu naught rho, and of course this is e to the minus j beta z h rho. Now, a thing to note is that this is the curl of h, so we're not quite done. Now we know that this thing is actually what we're looking for, so we equate that with this. So we get j omega epsilon naught es is equal to, I'm just going to leave it like this, j beta, we can simplify it after, minus j beta C over mu naught rho e to the minus j beta z a rho, it's a mouthful, es is going to be, I guess we can get rid of one of the j's. Or we can do something. Well, let's just, those two j's will end up cancelling out. Okay, so what happens is those two j's cancel out because j times j is -1, negative that is just positive 1. So these two j's end up just becoming 1, so they go away. So we end up with beta squared c over j omega mu naught epsilon naught rho e to the minus j beta z a rho, and this is volts per meter, even though these regard as units again. And this is A between A and B. Oh. Oh. That brings back memories, doesn't it? That field theory. Any questions about that? That was with 5 marks. So. Yes, the betas. When I start writing a little faster, they start the beta of them. They start becoming less beta. Pun intended. Okay, so next it asks. Sorry. Next it asks for the skin depth for the inner conductor. Rho less than A. So the skin depth for the inner conductor. Can anybody tell me what the skin depth for the inner conductor would be? Sorry? I can read the question to you again because it's given to you in the question. You don't really have to do anything. It tells you that the region between these two perfectly conducting coaxial cylinders, if they're perfectly conducting, the skin depth is 0 when they're perfectly conduct. Because when they perfectly conduct, they reflect everything. So nothing actually conducts at all. So it's funny how perfect conductors don't actually conduct. It's ironic, isn't it? At high frequencies, perfect conductors stop conducting. So once you get into like gigahertz range, if you have like a copper strip, it's not conducting very much. So that's why if you notice a lot of these circuits that you have, these copper traces always take weird shapes, is to prevent these kinds of things from happening. Because the resistance gets really high at high frequency. So you have to keep in mind, we're talking about high frequency. We're not talking about like copper for like 60 hertz. 60 hertz copper, sure, it'll work perfectly fine. But high frequencies, perfect conductors, 0. Well, that's something you should know. This is physics. It's not enough to know 100 equations. I agree with you. You have to know what these equations imply. So yeah, the skin depth for the inner conductor is 0. So yeah, that's 1 mark. So there, get that, get the drawing, and then get the whole first question. You're set. Now we get into a little more field theory related stuff, or sorry, electromagnetics related stuff, and it asks for the time average Poynting vector in that free space area using the obtained intensities. So time average Poynting vector, if you remember from either lecture or the last class, is 1/2 real ES, sorry? I don't know what he does. He has like 5 different P's, I know.
Yeah.
And then he'll have one is like a curl on it, one's like this, and he goes, no, this is, and then he goes, this is the time average, and he just doesn't make sense. I don't know. Whichever one he calls it. This is the time average Poynting vector. So just note, whatever he calls the time average Poynting vector, call this that. I don't know how he's making his P's. Because I would just add another subscript and write time average. Like, I don't know why he doesn't just do that. Give another subscript. Anyhow. So ES we have from the top, HS we have from the top. Now the thing about this to note is what? It's that cross product when you have single single dimension vectors, the cross product just becomes straight up multiplication. And you just have to remember that it's in the direction that is perpendicular to the two other directions. So if ES is in A rho and HS is actually in A phi, then we know that this is going to be in AZ. Somewhere in AZ. It's going to be either positive or negative AZ. And you can figure that out based on your right hand rules and whatnot. Or you can just memorize it, which I would not recommend, but some people do. So ES we have is beta squared C over J omega mu naught epsilon naught rho e to the minus J beta Z A rho. And this, we're taking the cross product with the complex conjugate of the magnetic field. So this is magnetic field is minus J beta C over mu naught rho e to the minus J, and I'm just going to write conjugate on the side, so I know it's conjugate, but I just want to have everything in front of me once. And so I want to keep in mind that this is this thing conjugate. Okay? And then we take the real part of the whole thing after. Okay, so the complex conjugate of this thing just becomes what? What ends up happening is we have that this complex term is actually going to become positive. It's going to be e to the positive j beta z. And we have to also keep in mind that C has told us, it's told us that C is complex as well. So C is going to be replaced by C conjugate. So, we guess we can start having fun and multiplying this thing across. So what we end up getting, well, I won't do it all in one step because that's going to be too much. So let's rewrite it as a conjugate first. B squared beta squared C J omega mu naught epsilon naught rho e to the minus J beta Z A rho times, or sorry, cross I should say, minus J beta C over mu naught rho. This is C conjugate. And this is e to the J beta Z. One thing to note with this stuff is that if I'm being asked for the time average Poynting vector, these complex terms should go away because it's a time average. Your time average should not be complex. So you'll notice the exponentials are going to multiply and they're going to cancel each other out. That should happen in the time average. That's why we take the conjugate. That's why it's defined that way, is because that ends up giving us a time average and not just some number, you know. So this is going to end up canceling with that. And so then you realize that the whole idea of writing real becomes irrelevant. Yes? Is it a different direction? I totally wrote it. Oh my god, I did. Sorry. It's not. It shouldn't be. Nice. It shouldn't be there. I got excited when I wrote the next one. I started writing the final answer before even doing the question. So essentially this becomes 1/2. Now the whole thing inside is real except for C. So the real part of C is just going to be the magnitude of C, right? So if I take magnitude of the conjugate thing, we're just going to replace it with the little bars and we're going to write C in between. Sorry, I lied to you. It's magnitude of C squared. No, it's not. C in the first term, sorry. It's magnitude of C, right. So the real part of a conjugate is just its magnitude, which I guess we should know. And it's silly of me to have made that. So this is minus J beta cubed C times this magnitude of C all over J omega mu naught squared epsilon naught rho squared. Okay. I hope we're good there. Now, of course, these two J's are going to cancel. And so that whole real thing, we can still write real, but the whole thing inside is real anyway, so I guess that really doesn't matter. So I guess we can just get rid of that part. He doesn't include it here. So this is... Holy crap, this gets messy. Anyhow. Sorry, I lost myself here. Made a mistake here. This should be positive. Anybody tell me why this is positive? Sorry? Exactly. Conjugate. Should be positive. Right? So that's why I kind of lost myself there. Beta cubed. Magnitude. Well, we don't even need to write magnitude of c, but we'll write magnitude of c just for the sake of it, because we know the c on the initial one we have is c times c. Magnitude is magnitude c squared, because it's the same thing anyways. But you write the magnitude there just to make him happy, kind of like we write the arrows. The arrows on the I don't know why the arrows are there. I still to this day do not know. Nobody else does that. So, yeah. Does anybody remember why he does that though? But I certainly do. But the direction, it's a closed loop. It doesn't matter which direction you take. It doesn't matter though. I know he told us that too. That's when I did it, but I don't remember the reason was. But the thing is, it makes no sense because the direction is irrelevant. Oh, apparently there's a half mark for this thing right here. This thing for writing magnitude like that. So make sure if you get that, make sure you write the little magnitude signs. Because it says one half. It says includes 1/2 mark for magnitude c squared. I kid you not. And then there's half a mark for this thing. Half a mark there. So make sure you don't forget little details like that because that'll kill you. And if that's there, and for example, if I'm marking you guys' test and I see that, I don't want to take marks off of that, but I'm gonna have to. And it's gonna kill me to do that just because it is, and it's just so silly but it's at the same time it's so silly for you guys to lose marks on that, right? Because it's like those are free marks. Even if you get the thing wrong, but you write that there, you're still get the mark for that. Like if the rest of your expression is wrong, but you still wrote AZ, you'll get that half mark there. Write it in general form, right? Like P, or write like P naught AZ. If I'm marking it, I'll give you the mark. But I can't guarantee I'm marking. You guys better hope I'm marking the hardest question, I guess. Because I'm not going to be overly, anal about it. But there are certain things I guess I'm not going to be able to present. Yeah, just write a capital P, AZ. I'm good with that. I'll write that circle a bit. Yeah, that's in the right direction. The direction is right, at least. Now it asks for... Holy crap, these questions are going in there. Total... time, average, power transmitted by yes, average power transmitted by the cable. Okay, now this thing we have to integrate, right? Because when you want to find the total, you usually have to integrate across some surface. This part isn't too difficult. So P. Now notice it's not going to be a vector because it's going to be the total time average power. So now power itself is not a vector. So this thing is going to be integrated across this circle. Yes, there is. I forgot them totally. That's because he forgot them. Watts per meter squared. Just think about this. You have volts per meter squared times amps per meter. Sorry, volts per meter times amps per meter. The volt times amps is watts, and then your bottom becomes meter squared. So that should be there. Thanks for pointing that out. This is just your P average dot ds. Now, what's the surface though? I guess that's the question. What surface are we integrating? Where's the power transmitted from in a coax cable? Holy crap! More things we need to know. Where's the power transmitted? How do coax cables work? Yeah, so where does the signal come from? The middle, right? So now we need to integrate this power thing across the middle surface. So it's important to realize that, so you're not integrating over the whole thing, because that's integrating over free space. So the power transmitted by the cable is... But here's the thing. Didn't we say there's no... There's the skin depth is 0? So it doesn't conduct. So that means the power is not there. Where is this power defined though? Where are E and H defined? Let's look at that. Whoa, 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 what's happening? What's happening? What are you doing? Whoa, whoa, whoa. What's going on? This thing. And this thing. And so then where is my Poynting vector defined? Anybody? If E and H are defined in these two regions, or this single region I should say, they're both defined in the same region, then where should my Poynting vector be defined? Same spot. A to B. So then the only surface I can integrate is A to B. Now you see how I assumed that I was thinking about how coax cables actually work, and I made the wrong assumption initially. But again, we should be able to check our understanding as we go through the question. Like I said, the skin depth is 0, so does it really make sense for me to integrate over the thing where it's not conducting? Then why would there be power? Because the question's asking me for how much power is transmitted. Why would I calculate this Poynting vector in a different region and then integrate it over a region that's not conducting? Right? And so, I mean, initially I made the wrong assumption, which happens to me on tests all the time. But then you go back and you reason with it, and you see it's not actually making sense. Is the thing that I'm trying to do actually physically reasonable to do? Not really, because if I have no current flowing through there, I don't really have a power going through there, I don't have an electric field, I don't have a magnetic field, nothing. It's perfectly conducting. Perfectly conducting in ELE 202 means great. We're going to go there. But we're not going there here, because this is high frequency, you have to keep in mind. It's not written, but it's always implied. So, this surface then becomes what? Rho equals A to rho equals B, and phi equals 0 to 2 pi, which is how we define circles, right? Or cylindrical areas, I guess we can say. The phi from 0 to 2 pi defines the entire circle, and then the rho between A and B defines that thickness that we have. Again, if you have the thing in front of you, I guess you can see that. And what are we integrating? We're integrating this expression we have up here. So we're integrating 1/2 eta cubed c squared omega mu naught squared epsilon naught 1 over rho squared a z. And how is this thing defined here? The differential, he gives that to us, I think, in this. Definitely. Nope. Get this, he gives you the volume, and he gives you the line, how to integrate in different coordinates, but doesn't give you the surface. The one thing you need is really. But no, you can still figure it out from the things that are given, because you know that whenever you have a rho, or a d phi, you always have rho d phi, always. And then this is going to be d rho, right? Rho d phi. Well, no, it's given you. It's a given here. If the line is given, you get the thing for the parameters for the actual components. So it gives you that dl in cylindrical is d rho a rho plus phi d phi a phi plus dz a z. So now you just take the two components that you need and you multiply those two components together. Because if you have a line and you were to multiply that line across some thing, you would end up with a surface, right? Right, but some people forget the rho in front of it, that's the thing. The d rho d phi makes sense, right? That's what you think. That's not what everyone thinks though. So I'm trying to give everybody a foolproof way. It's written there on the sheet. And if you have any questions about that, you can ask me about that. And this thing is also in AZ, because keep in mind the surface is also has a vector sign, right? You notice this thing right here has a vector sign. So the surface vector has to also have a vector, so it's AZ. So when you take the dot product, it becomes just a single value, because the dot product's going to give you a scalar, right? Exactly. You want some time average power over something, and you want power, so it's. Sorry? This is not a vector. It will not be, because it's going to be how much is transmitted, and so that shouldn't be a vector. Exactly. So if you integrate this and you end up with a vector, you've seriously done something wrong. Go reconsider your answer. So let's start by taking all this out. I'll just put that in there as well. So let's take all this stuff that doesn't depend on what are we integrating? Whatever we're integrating. So whatever's constant, let's pull out. And this is from phi equals 0 to 2 pi. And so all I have left in there is 1 over rho squared, rho d phi d rho. And so what ends up happening is this one ends up getting rid of one of those. And so I'm left with beta cubed c squared 2 omega mu naught epsilon naught. So essentially the integral from phi just becomes a multiplication with 2 pi. Because nothing else depends on phi. Does that make sense? Because if I integrate d phi from 0 to 2 pi, all I do is just multiply by 2 pi. So I'm going to go ahead and multiply that 2 pi here. So we can stop carrying that term. And so then what I'm left with is rho equals a, rho equals b, 1 over rho d rho. And now this integral becomes what? What's the integral of 1 over, sorry? What's the integral of 1 over x? Ln, exactly. Ln. So then what I'm going to do is if it's ln of rho, and then you evaluate that at b minus a, it's just going to become ln b over a. Because of our log properties. So this becomes beta cubed magnitude c squared 2, well our 2's are going to cancel, so let's just not carry those anyways. Omega mu naught epsilon naught, this pi comes in here, and then I get this ln of b, not beta, b over a, and the units of this thing should be watts. Not watts per meter squared, because notice we integrated over the surface. So it's essentially like we multiplied over a surface. So again, some things to note: if you do this integration and you end up with a vector, you've done something wrong. If you do this integration and you end up with units of watts per meter squared or watts per meter, you've done something wrong. This thing should be a scalar quantity, not dependent on. It shouldn't vary with any parameters. So you notice this is all constants. B is a constant, A is a constant, all the other things are constants. Nothing here is varying. And so these are sort of things you can look at and to make sure you've done it right. Which is the hard part, right? Like, who the hell knows the theory? Just try to remember everything. You can only get so far with that. So that was worth how many marks? That was probably worth 3 marks. 5 marks for that. Where's that thing? Apparently there's like 1.5 marks for integration, so if you don't get the integration but you did the rest of it right. I don't know, I'll make the marking scheme. It's just what? Part F? Power loss. What's the power loss? Power loss per unit length. I like that. So that's 1 mark. Gee, holy crap, this guy just says man, dude. Frequency domain, surface charge density, rho SS on the surface of the inner conductor. Okay. Surface on the surface of the inner conductor. Rho SS is the surface. It's the frequency domain surface charge density. So rho s is the surface charge, and then you put the extra s to say it's from frequency. So he's been nice on this one. He's giving you the boundary conditions. They're given down here. So essentially you just apply boundary conditions on that surface, and you can find what the surface charge density is, because it tells you... What does it tell you? Boundary conditions are given as... Here. So it only one of them actually has rho s in it. So it's d1s minus d2s. But the dot product of a unit vector going from region whatever to whatever is actually rho ss. I should hope. Or is he going to use the other one? No, he told me to use this one. Anyway. Okay. So d1s, yes. A is n21. That's to denote a unit vector going from region 2 to region 1. Remember boundary conditions, which is I think chapter 6 from ELE 401, which everyone's probably looked at. AN21. AN21 is a subscript, so it's a unit vector that's normal from the region 2 to 1, which is the two regions that are creating this boundary. Okay, so we get that rho ss. D1s is going to be epsilon naught es. At rho equals a. And ds2, so what I'm imagining here in this case, I probably should draw it out here, is this is the sort of thing we have. And I'm calling this region 1 and this region 2. So the region 2 is the solid part of the conductor. Okay? The other one's free space. So that's why I have epsilon naught es. Because I'm going from free space into the conductor. Now you'll notice if I go into the conductor, what happens? I have no electric field there. So this term becomes 0. So it literally becomes d1s dot an21. So what's that unit vector going from outside to inside? I want it to be normal to the boundary, so it's a rho. Right? Because a rho is always in like this, where it's like normal to whatever thing you have. A rho goes out this way. So if I'm coming in, it's just going to be negative a rho, which for some reason he hasn't done here. Okay, anyhow. Should be negative a rho, I believe. I don't remember how it's defined exactly though. So let's just keep it the way he's done it, just so we don't, mess anything up. So this should be dot a rho then, okay? Because again, like I said, I'm not sure how it's defined. If it's defined as 1, 2, with the boundary going that way or this way. I don't remember which way they define the vector, but literally it's the difference of a minus sign. If somebody has a textbook, I guess you can double check that and figure that out. It's like chapter 6 or something, or 7. So this epsilon naught es, this equation I have all the way up here somewhere. So I evaluate es at rho equals a, and I end up with beta squared c over j omega mu naught a, because rho is in the denominator there if you remember, e to the minus j beta z. And this thing is a surface charge density, so I should have coulombs per meter squared. But again, he hasn't included yours. No, this is the electric field. The electric field didn't have the magnitude. That was in the Poynting vector. So if you go back up and you look at how we defined E, you'll find that we had the rho in the thing bottom, but the C was still complex in that case. So that's the surface charge density on the... What was that? I don't even know what that was anymore. Of the inner conductor. Yes, what do you want? Units? Oh, coulombs per meter squared. Charge density, right? On a surface? On the surface, right? G, so that's H. Now H asks us for the surface current density Ks on the inner surface of the outer conductor. So he wants this thing right here, that inner boundary there. So what's the surface current on the inside of that? Because there will be some surface current there. And again, because he asks for Ks, and if you look at your equations of your boundary conditions, only one of them gives you Ks, so you know which one to use. And in the other case, only one of them gives you rho s, so you know which one to use. So I guess it's nice in that case. So what do we have? We have, this is the boundary condition, is h1 s minus h2 s cross kn1 2. Notice this is not 2 1, this is 1 2. So it just depends which regions we're going. So it's probably going to go the other way. But again, it's all just relative to which way you defined it. If I define one region to be this thing and one region to be that thing, it should end up giving you the exact same answer. It doesn't know which way you're going. So this thing, KSS, because it's in the frequency, SS is going to be HS1 evaluated at rho equals B with cross product of A rho. Now again, you notice that we have, if you consider your two regions, inside the conductor you should have nothing. Even the outer conductor, it tells you that it has some finite thing, because it tells you it's perfectly conducting. But again, you should have no magnetic field inside there because it tells you it's perfectly conducting. So you should only have one term here. So you have this HS1 for H1 because it's perfectly conducting. And if it wasn't, then it would just not be reasonable to ask you that question because it would take forever to solve that question. Trust me, I know I have a class that we're doing that, so it's a pain in the ass. So what we end up getting is HS1 is in which direction? Which direction do we have? HS is in A rho. So if the HS is in A rho, then he takes the cross product of positive A rho. How does he get AZ? I don't know. Let's just see what we have up here. Just want to make sure. HS is an A phi, but he's written HS. There's a typo in his solution. It should be A phi cross A rho. It should give you AZ. And I'll comment on how you can figure that out too, just in a sec. So we have this J beta C over mu naught B, because again we evaluated at B. Then we take phi cross rho, which gives us AZ. So we have e to the minus j beta z AZ, and this again should be coulombs per meter squared. Okay, now how do you figure out if it's going to be, like we just had a little bit of a hiccup there where we didn't realize which direction it's supposed to be in. How do you figure it out? Think about this. If this thing is my conductor like that, we know that the current should be going out of the page or into the page. That's how cables work, right? So it should be going in one, it should be going out or it should be going in. So if I've defined A rho as that way and I've defined A phi as going in this circular direction, then that means my current must be, logically speaking, coming out. So, like again, there's a typo, it's written wrong in the solutions. It says HS is A rho here in one of these solution parts, but I wrote it down correctly here in our notes, but he didn't do that here apparently. And so, you should be able to reason with these things and figure out, like, hey, is it right or wrong? Part I, and this is the most interesting part, but we're not going to do this because it says bonus. And there's no answer given for it. So it says the characteristics of the propagating electromagnetic wave within the coaxial cable. What are the characteristics of the waves inside the coaxial cable? I don't know. I don't know what he's looking for because he hasn't given any answer. He just says bonus. You could go on forever for it. There's no. That's not really a question worth asking, in my opinion. That's why it says bonus. Okay, so we have like 20 minutes left, and then we have this last question, which is identical to the one I did last week, so I'm probably not going to do that, just because it's literally the exact same thing with a different electric field. And I think it would be worth your while to actually do it, because you know how to do it, you just haven't seen the different numbers, and you can compare the results with my solution, or like the procedure with my solution. If there's any other questions, we can look at those right now. If you have anything else you want me to cover, anything I didn't cover here, anything here that is unclear, any parts of this that didn't make sense. So we're good? Cool.